Okay, thank you for joining again. So if there is any doubt on regarding the C7H7 ligand and the reactivity, please let me know before we move to C8H8 ligand, which is the next part of our discussion.
Why is this RHCO2 Cl twice?
Sorry, can you please
This
repeat?
metal bond, ma'am.
This metal, Fe and rhodium, right?
Yes, ma'am.
Yeah,
Why is this happening? What is this RHCO2 Cl twice doing?
this is another complex. This you can consider as another complex where rhodium is having a carbonyl group. This one complex you are looking at in the iron case, which is a mononuclear, right? Where only one metal center is there in binding with C7H7 and three carbonyl groups are there. We are giving another complex, which is a dimeric. And in that dimeric, we will be having a rhodium and rhodium binding with each other, having a bridging between the chlorine and chlorine. Now, when we are giving this particular source and already our substrate, which is having a C7H7, first point that has to be noted that the coordination of C7H7 has not been fully utilized in this particular complex. That means it has four more ligands that can bind with another system, which is your any other metal center which requires four electrons. Secondly, whether iron will bind with another metal or not, because it is having an extra electron, so it can easily make a metal-metal bond with another metal center. Similarly, in the second case, which is having this 2 means it is making a dimeric structure. So we have 2 rhodiums, 4 carbonyls, 2 chlorines, and here half of the molecule is going out and only half is remaining as such because iron can make one single bond with your rhodium. And rest of the 4 coordination, which was fulfilling in the dimeric structure, now it is being fulfilled by your C7H7. That is where it has been said that whenever you have a partial coordination of your C7H7, that would lead to have a metal-metal bond. But it is very much necessary that your other metal center should have that particular charge or any vacancy that it can make a single bond or double bond with your another metal center. That's where the single metal bond is being happening. If you calculate the 18 valence electron, it would be fulfilling the total roles. It's a simple process. Like earlier case when I was telling that when we are going from, say for example here, so when we were having earlier eta 3 hapticity, we were maintaining all the ligands were there. As and when I'm providing a source of light, my two CO groups are going out. That means I'm losing 4 electrons, and for maintaining that, it took up the electrons from your C7H7. Similarly, in this particular case, earlier we have a stable complex of iron, which is 16 electron valence or 18 valence electron. In this particular case, also it would be 16 or 18, maintaining its stability and having all the electrons. Now, when I am treating it with this one, it is losing out other electrons or bridging ligands like Cl is going out, 2 carbonyls are going out. It has to maintain its electron density around it. So it makes a bond with iron and it takes 4 electrons from the C7H7, which were free, which were not being utilized earlier.
Yes, ma'am. Clear.
Okay. Okay, so if everything is clear, now we can move ahead to C8H8 ligand. And after that, we will be talking about the preparation, binding, bonding properties, and the reactivity, of course. So C8H8 we are starting with as a ligand. So we have actually covered the allyl ligand. We have taken C3H3, we have taken C4H4, C5H5, C6H6, C7H7. Now we are coming closer towards the C8H8, which is nothing but your cyclooctatetraene, which is called as COT. So there are certain features that we need to keep in mind. The first feature that we have is this COT resembles the alkyne ligands having the triple bond. It doesn't mean that it is having a triple bond, but the number of double bonds that we are having, it resembles to that of alkyne ligands. The cord can coordinate. So there are different ways of getting this cord coordination. It can coordinate as a tub shape, 8 electron donor, tetraolefin ligand, or it can coordinate as a planar, 10 electron donor. So you already know the Huckel's rule of aromaticity, which is 4n pi plus 2 electrons. So it can be a number where if I'm saying that it has to be, if 2 pi electrons are there, so it would form like this way, 4 into 2, 8 and 10 electrons, something like that. So once it accommodates 2 more electrons, that means got 2 minus charge, it would take up the 2 minus and therefore it would make a 10 electrons, and that becomes a very stable species. So this is a cot 2 minus, meaning C8H8 2 minus, which is 10 electrons. This is planar and this is aromatic as well. Another feature is cord displays various coordination modes, meaning the hapticity. So it can bind as eta 2, it can bind as eta 4, eta 6, and eta 8. There are total number of 8 carbons. It can go in an even number wise. Also, cord can display eta 3 and eta 5 as well, which is an odd number coordination modes. But this is possible only in binuclear system, where we are having 2 metal centers. In those systems only it would undergo eta 3 and eta 5. We will be seeing the examples later. And the last point that we have is cord can bind terminally as well as a bridged ligand. That means it can be, say for example, we have a cord. So it can be easily bound with the metal, or it can be working as a, like this particular way, the 2 here and 2 here. So this is a bridged one. This is one such example. That means eta 4 at one side, eta 4 at one side. Here it is eta 8 for one particular metal center. Or it can be another coordination modes also. But the take-home message is the cord can bind in both ways, as a terminal ligand also and a bridge ligand also. So moving ahead, now we have the preparation methods. So firstly, we are talking about the preparation methods where we have to make use of a planar H8 ligand. That means it would be a C8H8 2 minus. So the one stoichiometric equation that we have is, if you are using a 0.2 titanium C4H9, it's a oxide with 0.4 C8H8 in presence of folious acid, which is aluminium based triethyl aluminium. And when we have this particular system, it would form a C8H8 3 molecules connecting with 2 titanium. That means it's a binuclear system. If we have this kind of stoichiometric ratio. Now, if we change the stoichiometric ratio to 0.2, titanium OC4H9. This is a substrate or a salt. You are using now two molecules of C8H8 and two molecules of AlCl3 It would give you a monomeric structure of C8H8 twice. Therefore, what it means to say, the stoichiometry really decides the composition of your complex. So how many moles you're giving and how many moles it is actually reacting, it depends. It really decides like how your complex is going to be. Is it going to be a mononuclear center or it is going to be a binuclear system? So this was the first way of treating it with cod and in presence of a Lewis acid and you're making a complex. Another way of doing it is by taking a hafnium chloride, which is a salt, treating it with magnesium and 2C8H8. It would end up firstly making a Grignard reagent and ultimately it would form a C8H8 whole twice hafnium and 2 MgCl would go out. Now, another way that we can think of is if we are taking another different metal salt, which is zirconium chloride. Firstly, you're treating it with K2C8H8. It's K potassium positive. It would give your C8H8 as 2 minus. This is 2 positive. And firstly, and secondly, you're treating it with methyl 5C5 positive and negative in THF solvent. That means you're giving it a source of both the ligands. One is cyclopentadiene as well as C8H8. So what it would do, it would form a complexation with both the systems, C8H8, zirconium chloride. So this is your complex. Now, in presence of lithium R, which is positive and this is negative, since lithium can easily take your chloride, lithium Cl would go out and R would coordinate with your zirconium, making Me5C5, C8H8, zirconium bound with your R. R could be any group, alkyl group. Or if you're reducing it, right now it is in a oxidation state of this is -1, this is -2, and this is -1. So it is giving you an oxidation state of +4. Now, when you're treating it with sodium Hg, this is a reducing agent. And reducing agent would give you an electrons, and therefore it would convert it from +4 to +3, making Me5C5, C8H8, just the zirconium as Cl is being taken by the, as in when sodium will give you one electron to the zirconium, it would form a sodium positive. This sodium positive can easily take your chlorine, making an NaCl out. I hope this is clear. If not, please let me know.
Clear, ma'am. It's clear, ma'am.
Okay. So moving ahead, now we have some structural properties of the C8H8. Could be a bit complex, but just a second. Okay. So now we are going to talk about. So we have seen the preparation methods for how to make a transition metal complex with C8H8. And now we are talking about the C8H8 complexes, their structural properties. So, say for example, I have a titanium complex with C8H8 whole twice. Here, it actually exists in form of titanium bound with eta 8 C8H8, one molecule, another eta 4 C8H8. So it is not that both the centers are, because if you count, it would give you an 8 electrons here. Titanium is 4 electrons, and 4 electrons are coming from here. It's 16 valence electrons, which is required. If it is totally 8, 8, that would be crossing 8 plus 8 and 4, that is 20 valence electrons. So titanium in this particular case makes a 16 valence electron stable complex. So here C8H8 occurs in two different hapticity modes. Or you can say a coordination modes. At one place, all the 8 centers are involving, and in other place, only 4 centers are involved. So another property for this one, in eta 8 C8H8 system, we know that it is planar. So planar meaning all the CC bond lengths would be equal. And in planar system, we know that it comes in a range of 140 or 141 picometer. In eta 4C8H8, this is a puckered system. It's not a planar anymore. It would be a kind of system like a tilted one. 1, 2, 3, 4, 5, 6, 7, and 8. So this is your bucket system. And having double bonds, right? So in this system, it is a kind of butadiene system. So you have also seen the kind of, we have a butadiene. So this makes like a butadiene system. So which is not a planar. And the third property that it is having, in solution phase, we see a fluxional behavior. Fluxionality we have seen, for example, if we have a possibility of a ligand going from eta 5 to eta 7 or eta 7 to eta 5 and changing the hapticity more oftenly, and that is called fluxional behavior, where the exchange and the rapid exchange is happening. Because of that, if we record an NMR and if it is recorded at, say, for example, room temperature, the fluxional behavior, if it is very fast, you won't be able to identify which bonds are coordinating with, which centers are coordinating with the metal and which are not coordinating. So it would give you an average environment. For example, if I'm having we'll take a chord only. So if I'm saying I will label all the bonds, it is A, B, C, D, E, F, G, and H. Now I'm saying I'm only coordinating these bonds with the metal center, which means these hydrogens, these protons are bonded, which is of C, D, E, and F. So only these 4 which are bonded with the metal, these 4 should give me one signal, and the other 4, which is A, B, H, and G, they should give me another signal. NMR I'm talking about. But in that case, the fluxionality changes. You might not be knowing that it would exchange the partners like C, D, E, F. Rather than that, it would go and bind with A, B, H, G. And therefore, it would give you, due to the fluxionality, where the rapid exchange, fluxionality means breaking off these bonds and then coordinating with other bonds. If it is very fast, so in NMR, you will get an average environment and you will only see one signal for all the 8 protons of C8H8. So this is for all the cases. If it is eta 4 system, if it is eta 8, you will get all the one signal only, because all the 8 coordinations are there. In eta 4, eta 3, eta 5, eta 6, any coordination, not just this particular ligand, any ligand which is having a fluxionality behavior, where the metal coordination can be exchanged with the other centers, And once that happens, you will end up having a very fast exchange, and you will end up having only one signal. If at all you froze your sample, if at all you record the NMR at low temperature, that means you are restricting your fluctuality. You are making the system such a way that whatever the coordination it is having, if it is having the coordination with C, D, E, and F, be it in that state. And then you can see the environment around C, D, E, F is different compared to the ABHE, and therefore you will end up seeing two signals. That can happen at a very low temperature, not at room temperature. In certain scenarios, at room temperature, we don't see much of the two signals. Only one signal is there. So this is the major properties of C8H8, where we saw that. So we have taken an example of titanium C8H8, where it is having two different hapticity. One is eta 8 and one is eta 4 to make a stable 16 valence electrons. When we are talking about eta 8, that's a planar system. And when we are talking about planar system, all the carbon-carbon distances which is having an olefinic bond, this is having a distance of 141 picometer. Pico means 10 to the power minus 12 meter. That's a distance. And when you're talking about eta 4, that's a system which is resembling the butadiene system. That's a puckered ring, and that's non-planar. And the bond distances will be different. And in solution, fluxional behavior occurs. Whatever the eta 4 is there, that can go to eta 8 and vice versa. And you end up having a one signal in NMR solution. Now, moving ahead for the fluxional properties as we were mentioning. So we will look into the fluxional properties. So if I'm taking iron carbonyl system and treating it with C8H8 in octane solvent at 125 degrees Celsius, so what would happen? In this particular case, this is already an 18 valence electron, right? So how we can accommodate this one? If iron is going to have 3 carbonyls, that means 8 plus 6, already 14 is there. Only 4 more electrons can come. That means eta 4 C8H8 is going to bind with the iron system. So it would end up making 18 valence electron. Now, as we said, fluxionality appears that is observed in eta 4 mode. So in this particular case, the adjacent bonds, say for example, iron, and here you have I'm just making this system, or you can make a bucket system also. This is butadiene, and you can expect your binding like this way. So this is an eta 4 substitution. Now whatever the adjacent bonds are there, adjacent double bonds are there, they undergoes a very rapid exchange. Adjacent double bonds in the coordinated eta 4 system, they undergo rapid exchange, as I said, which is your fluxionality behavior. So it can go and work like this way, that now my metal center is coordinating with these 4 bonds, these 4 centers. Therefore, it would give you only one NMR signal. Even at, I was saying, very, very low temperature, even at minus 150 degrees Celsius, it is giving one NMR signal. So you can imagine that fluxionality is happening at such a faster rate that even at lower temperature as minus 150 degrees, we're not talking about minus 10, minus 50, we're talking about minus 150 degrees. At that temperature also, it is not able to differentiate between 4 different centers from the ones which are coordinated with metal, because there is such a rapid exchange. This is the feature that comes from the fluxionality. So sometimes when we see the NMR, we are expecting the metal center to be whether it is in eta 4 and eta 8. That would be very difficult to comprehend, because even at room temperature, you are seeing one NMR signal, and at low temperature, when, say, for example, you recorded at minus 100 degrees, and you are still seeing one signal, you might be expecting that it is having an eta 8 configuration. But you need to then recalculate the valence electrons, see the bond distance if it is possible, if it is crystallizing, the bond distances are same, or bond distances, if it is same, that means it is in eta 8, which is not possible in iron case. In this case, if it is having different bond distances, and this is not a planar ring, if it is a puckered ring, it is very, very clear that, okay, at even low temperature also, it is undergoing fluxional behavior, rapid exchange is happening. Therefore, all the 8 centers are coming as a one signal. So I hope this is clear. If not, if there is any question, please feel free to ask it now itself before we move ahead.
I'm clear about it, ma'am.
Okay. So now moving towards it can, as I said, that it can act as both bridging as well as the terminal ligand. So we can see another property of C8H8 complexes in bridging mode. So the example that we are taking, you take 2 molecules, 2 moles of chromium chloride, and treat it with isopropyl magnesium bromide. This is an isopropyl group. This is a Grignard reagent, which is a source of your R group. And you're taking 3 moles of C8H8. So this reaction actually exchanges your ligand. So it would take up C8H8, and therefore it would release as a MgBrCl in an ethyl diethyl ether source. So ultimately you will end up releasing MgBrCl, and isopropane group will go out. It would give you a dimeric structure of chromium 2, C8H8O3. So this is a bridging system where one of the groups would be in bridging form. Similarly, if you are taking a tungsten Cl4, treating it with K2C8H8, which I've already mentioned, this is 2 minus and this is plus, in a THF medium, it would end up forming W2C8H83. Here, C8H8 is acting as a bridging ligand. It's not terminal ligand anymore. So it would act as a bridging ligand between these 2 metal centers. So how it acts as a bridging ligand, we'll see the structure now. So actually, in both the systems, what if the bridging ligand is there? The terminal rings, they would be having a eta 4 type, and rest other bonds would be taken up by the bridged one. See, for example, if we have one group like this way, another chord like this way, and okay. So I'm not making the double bonds, but I'm just highlighting the atoms. Okay, so if we have 2 metal centers, one metal is center here, another metal center is here. Now, in the terminal, because these ones are terminal, which is only going to bind with the metal center. The other one is the bridged one. So this is a bridged one, bridged C8H8. These 2 are terminal ones. And in terminal ones, it will occur as a eta 4H8. That means 1, 2, 3, and 4. Only these 4 centers are going to bind with your metal. Similarly, this side, 1, 2, 3, and 4. The other 4 will not participate. And here, all of them would coordinate with everything. I'll make it with a different color, maybe green one. So 1, 2, 3, 4, and 5 over here. And there would be a bond between two metal centers. Similarly, other side, 1, then 2, this is 3, this is 4, this is 5. So here it is taking 5 from here, 1 bond between metal centers, eta 4 from your terminal bonds. So generally in this particular case, 3 metal bonds, triple bond is considered. So if 3 metal bonds are there, that means it is going to have a 18 valence electrons. We can consider a chromium system where chromium is there and it has taken eta 4, that means 4 electrons from here, and chromium is having 6 electrons, which is already a 10, and now it needs to have 8 more. So as I said, 5 it is taking from these centers. So 5 coming from one part and 3 more are left, and that it takes from a 3 triple bond. So 10, 5, and 3, which is 18 valence electrons. So the take-home message, the terminal one makes the eta 4. The bridged one, all the 8 centers are involved. If metal triple bond is involved, then it would form an 18 valence electron, and fluxionality is again observed here, and only one type of signal is occurred, which appears at 5.26 picometer. So I hope this is clear. Only the distance that you need keep in mind. Chromium distance is 221 picometer, whereas if you have a tungsten metal center, that would be your 237 picometer. So this is the way bridging C8H8 ligand occurs and how the hapticity. The terminal ones would occur as an eta 4. All the 8 centers would participate, making a 5-5 bond with metal system, giving the 5 electrons to each center, making the 18 valence electron configuration. Right? Now, another example of this bridging system, we have a nickel complex. So in case of nickel complex, bridging is little different. So we have this kind of system where we have 3 olefins and binding with nickel. We are starting with this one. And now it is being treated with C8H8 at minus 40 degrees Celsius. That means it's highly reactive. So it has to be given a very low temperature. What really happens when we have similarly on the other side? So in this case, when it forms a bridging ligand, this metal center only interacts with the 3 centers at one go. Similarly here, so here both nickel is eta 3 C8H8 allyl type of coordination. So as I mentioned in earlier case, generally chord is being seen as eta 2, eta 4, eta 6, and eta 8. And in some cases, where it is forming a bridging complex, there you can see and expect it to have an eta 3 or eta 5 coordination range. And this has been given by Kruger in 1976. So if there is any doubt, please let me know before we move to our next topic of heterocycles, which is thiophene and pyrrole systems.
It's clear, ma'am.
Okay. So moving ahead with our next topic, which is from the lecture 34, and that is metal pi complexes of your heterocycles. We already very well aware of what is heterocycle, anything which is apart from the carbon and hydrogen, meaning if I am having a C5H5, this is your C5H5 minus, and if in that carbon place, if I put a sulfur, that becomes your thiophene. If I put a nitrogen with proton, that becomes your pyrrole. And if I put an oxygen, that becomes your furan. So this furan, pyrrole, and thiophene are your heterocycles. So we are going to talk about that sulfur, selenium, and tellurium heterocycles. Generally, we are going to see here, and we will be starting with thiophene, which is nothing but your C4H4 sulfur S. And this is isopi electronic with your CP ligand, which is cyclopentadienyl C5H5 minus. Another thing is thiophene C4H4S. This is weakly basic compared to like benzene. It's not basic, not much basic. And it makes a half sandwich type of complexes. We already know what is half sandwich complex. Sandwich complex, if something is having a similar ligand like CP groups on both the ends, whereas if another way, one side it is CP, another side it is having either carbonyl or any other ligand. So these kind of systems are sandwich complex. This is your half sandwich complex. So this also we have might be we might have read. We have read it. I don't know, remember which lecture we have read it, but in one of the week sessions we have discussed this also in details. Okay, so here what we are trying to say now, we need to see how it is being formed, the preparation. So this is a half sandwich type complex. We are taking a thiophene, the liquid, and we are treating it with chromium carbonyl at an 85 degrees Celsius. So what it will do, since we said that this isoelectronic with your C5H5 minus, that means it gives you 6 electrons. If it is giving 6 electrons, 3 of your carbonyl groups have to go out since you are giving a thermal energy. And when it is being treated with this way, this is CO, another CO, and CO. And here, your distance between chromium, carbon thiophene is 220 picometer, whereas distance between chromium and carbon of your carbonyl, that is 177 picometer.